The next thing I want to look at is the error that is produced because of the polynomial, Taylor polynomial. So I have several graphs for you of the cosine Taylor polynomial or the Maclaurin polynomial. So this right here is the original graph, and this is when n is equal to 0. So you can see centered at 0, it's only good at 0. And then this next one is when n is equal to 1, so this would be a linear. And so this right here is going to be, well, actually it's a quadratic because when it's n is equal to 1, you end up getting 0. And so this is going to be n is equal to 1 so that it hugs it a little bit better. And then the next one here is going to be n is equal to 2. And then you have n is equal to 3, n is equal to 4, n is equal to 5, 6, 7, 8, and so on. So this is for the cosine graph. Okay, so what I want to look at are the errors that are occurring. So if you can look at this table here, and you can see that the bottom row is the one that is the actual value. So f of x is equal to the cosine of x. So at 0, you can see that the 8th order Taylor polynomial and the 4th order and the 2nd order, they're all good, right? If the actual answer is 1, and then you get 1 for all of these. At 0.3, so now we're getting a little bit farther away from 0, you can see that the actual value is 0.9553. And then for the 8th order, it's exactly the same. The 4th order, it's exactly the same. But then for the 2nd order, it's slightly off. Okay, and then move to 0.6, and you can see that the original one is 0.8253, so it's good for the 8th order, but then it's getting a little bit off here and here. Right, and then same thing with the 0.9. Now we're getting a little bit farther away, and you can see that the 2nd order is very much off, even by 0.1. And so as you get farther away from where the center is, it actually gets worse and worse for the lower nth polynomial. But then if it's greater, then it's not as bad, right? So what we want to do now is to figure out the error that occurs, and error is the same thing as the remainder. So if you could turn your notes packet now to page 6. Okay, so we're looking at the nth remainder. The following is a notation for the error in the approximation of f of x is approximately p sub n of x. So the error is let r of n denote the difference between f of x and its nth Taylor polynomial. So this is the nth remainder for the Taylor series of f. R of n, the remainder of the nth polynomial, is equal to f of x, which is the original function, minus p sub n of x, which is the Taylor polynomial, and that is equal to f of x minus, and then in place of your p sub n of x, I'm just putting in the Taylor polynomial. So this whole sigma business is the same thing as what p of n of x is. In fact, I'll just write that in. Okay, so this right here, the whole thing is the Taylor polynomial. The following is called Taylor's formula with a remainder. So the actual f of x is going to equal the Taylor polynomial plus some remainder. Okay, so this is the Taylor polynomial, this whole thing right here. And then you have, this is p sub n of x. And then you have some remainder, something that's going to be left over. Finding a bound for r sub n of x gives the accuracy of the approximation of the Taylor polynomial with the original function. The bound for the absolute value of r of n of x is called the Lagrange Error bound. And this is named after a mathematician named Joseph Lagrange, and he is both Italian and French. So here's the theorem, and this is called the remainder estimation theorem. So I'm going to abbreviate it as RET, Remainder Estimation Theorem. And it states that if the function f can be differentiated n plus 1 times, so you have to go one derivative beyond what you are looking at on an interval containing the numbers x sub 0, and if capital M is an upper bound for the absolute value of the f of n plus 1 derivative of x on the interval, that is, the absolute value of f of n plus 1 of x is less than or equal to capital M for all x in the interval, then the absolute value of the remainder is less than or equal to maximum number divided by n plus 1 factorial times x minus x sub 0 raised to the n plus 1. Okay, so this expression here is basically the same as what we have for the Taylor polynomial, except we're extending it one term beyond that, right? So remember, it used to be just n factorial, but now we're saying n plus 1 factorial, and then the power is going to be a n plus 1. And this is for all x in the interval. Okay, move on to page 7. There are two important points about the accuracy of Taylor or Maclaurin polynomials for use as approximations. The first is that the approximation is better, usually better, at x values close to x sub 0 than at x values far away from it. So say that you had it centered at 0, it would be good around 0, but not if you get farther away. If it was centered at 2, then it would be best at 2 and maybe to the right or left of it, but not farther away. The second is that the approximation is usually better for higher degree Taylor or Maclaurin polynomials rather than those of lower degree. And that seemed to be true when I showed you for the cosine. So the 8th degree was much better than something with a 4th or a 2nd degree. We need some idea of the accuracy of the approximation. And so we have the exact value, which is the f of x, and that is equal to the approximation nth degree polynomial. So p sub n of x is the Taylor polynomial. And then you have some error, a remainder that is resulting, and so that is the Lagrange error bound. So if you were to solve for r of n of x, that is equal to, I'm just going to keep r of n on one side and then bring the Taylor polynomial over to the other side. So the remainder is equal to the actual value, so that's f of x, minus the Taylor polynomial, p sub n of x. The absolute value of r of n of x is called the error. So the error is absolute value of the remainder is equal to the absolute value of the function minus the Taylor polynomial. Okay, let's go through an example with e to the x. All right, so this is example 6. Use the nth Taylor Maclaurin polynomial for e to the x to approximate e to 5 decimal place accuracy. So I'm going to start off by deriving our e to the x. You may know it already, but it's always good to just derive it one more time. So I have f of x is equal to e to the x, f prime of x is equal to e to the x, and any power of e to the x is just going to be e to the x. Any derivative, I mean. So f of 0 is equal to 1, f prime of 0 is equal to 1, and f of kth derivative of 0 is equal to 1. Okay, so then I'm just deriving it over here on this side. So the p sub 0, the 0th polynomial is going to be 1. The first order polynomial, okay, working through this, I get 1 plus x. The second order polynomial would be f of 0 plus f prime of 0 of x plus f double prime of 0 times x squared over 2 factorial, which ends up to be 1 plus x squared over 2 factorial. And so the nth Taylor polynomial is f of 0 plus all of this, and then you have f of the kth derivative of 0 times x to the kth power all over k factorial. Okay, so I'm going to now write this using the sigma notation. Okay, so my sigma notation on this is f of the kth derivative of 0 of x to the k over k factorial as k equals 0 out to n. Okay, so then that would be the expansion of it. So e is approximately, or is equal to e to the first power, and that is approximately going to be 1 plus 1 plus 1 over 2 factorial. So I'm just placing the values in here for right now. Okay, so I have 1, and then I'm going to put in 1 plus 1 over 2 factorial. So I'm starting at 0, right? So 0 factorial is 1, and then it's 1 over 1. And then 1 factorial is 1, and so that's how I get 1 here. And I'm going to go all the way to n factorial. All right, so we want the absolute value of the nth remainder at x is equal to 1 to satisfy, it says to 5 decimal places. So I want the absolute value of the remainder at 1 to be 5 decimal places. So I'm going to take it out 1, 2, 3, 4, 5. And then if I want it accurate out to 5 decimal places, I need to have 5 out to 6 decimal places and then with a 5. Okay, so now I'm going to use my formula that I have generated on the previous page. So it's the nth remainder of 1, and then it's going to be less than or equal to, so I have some maximum value, capital M, all over, and then I'm going to take the next term over, so it's going to be n plus 1 factorial times absolute value of 1 minus 0 raised to the n plus 1. And so calculating this part right here, I get capital M over n plus 1 factorial, where m is the upper bound. All right, now if I use e, that is not a very nice number, right? So I'm going to choose the constant or the whole number that is greater than e. And so e is irrational and is 2.718. So then I'm going to choose the number 3, which will be an upper bound. Okay, so now I'm going to set it up as 3 is what my capital M is, divided by n plus 1 factorial is less than or equal to 0.000005. And then I'm going to reciprocate it and also multiply through by, or divide through by 3. Okay, so I just reciprocated, changed the inequality from less than or equal to greater than or equal to, and then I would divide by 3, because 3 would end up in the denominator, or I'm sorry, multiply by 3. So now I'm going to look at my factorials. So 9 factorial is 362,880, and then 10 factorial is 3,628,800. So the smallest value of n that meets the criterion is n is equal to 9. So to 5 decimal places. And so if I were to take e and take it out to 9 factorial, that would give me 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. And I keep punching in the numbers into my calculator, and I end up with 2.71828. So out to 1, 2, 3, 4, 5 decimal places, this is actually accurate. Okay, turn to page 8 and let's look at another example. All right, my next example is example 7. Use the remainder estimation theorem to find an interval containing x equals 0 throughout which f of x is equal to cosine can be approximated by p of x is equal to 1 minus x squared over 2 factorial to 3 decimal place accuracy. All right, so first of all, I have f of x is equal to cosine of x, has derivatives as all orders, so the first hypothesis of the remainder estimation theorem has been satisfied. So they gave me the p of x is equal to 1 minus x squared over 2, and I know that that is both the second and the third Maclaurin polynomial for cosine of x, because at the third one, it's just going to be 0. So you're going to choose the largest possible n, which is n is equal to 3. So then I set it up so that my absolute value of my remainder is less than or equal to 0.0005. That will ensure me a 3 decimal place accuracy. So then using the remainder estimation theorem with f of x equaling cosine and n is equal to 3 and x sub 0 is equal to 0, I put it back into that formula, which is the absolute value of the remainder of the third polynomial of x is less than or equal to capital M over, and I want to go one term over. So that'll be 3 plus 1 factorial. And then it's x minus my x sub 0 is 0, and then raised to the 3 plus 1. So that simplifies to capital M times x to the fourth over 24, because this becomes 4 factorial, and 4 factorial is 21. All right, so now I need to choose a value for m. And so since we're dealing with cosine, I know that cosine, it ranges from a -1 to 1. So capital M is the upper bound, so m is equal to 1, since the maximum value of cosine is 1. Okay, so now I can solve the rest of the problem. We can achieve a 3 decimal place accuracy by choosing values for x, for which absolute value of x raised to the fourth over 24 has to be less than or equal to 0.0005. And so if I multiply through by 24 and also take the fourth root, all right, so I did two things to get from here to here. I get absolute value of x is less than or equal to 0.330975. So that means that the interval would have to be between a negative 0.331. I just took away the absolute value, so I now made it as an inequality, double inequality. And then x is less than or equal to 0.331.